Hello everyone. Today I am going to explain on the analysis of the T-beam. So a small unit from the subject design of the reinforced concrete structure. So my presentation goes like this. First the T-beam and the L-beam theory. So next is the effective width of the T-beam and the L-beam. So rules for analyzing the T-beams. So one problem will solve. Next the multiple choice questions. We'll see some few multiple choice question. So let us see what is the T and the L beam is. So here in the picture you can see the reinforcement which is made ready for the purpose of the casting, means for the concreting. So in the field as you tell. So in the picture you can observe here there is a beam, so which is running longitudinally from column to column, and also there is a beam in this direction also, and the remaining portion, this portion we can call it as the slab portion. So one thing you have to observe from the picture is the beam and the slab are casted together, means concrete is poured at the same time. So actually in the field it happens like this. So when this beam and the slab are casted together, actually the beam will not be acting as an independent unit. So it will be combined with the slab. So the slab on the either part of the beam, see the left side and the right side of the beam, will be helping the beam in order to carry the moment. So that action can be called as the T-beam action. So that's why we will call this as a T-beam. The slab on the either side will be helping to resist the moment in the beam. So where it will help, how it will help, we'll see later. So but first thing is the slab will be helping to resist the moment. So that's why this is called as the T-beam. So if you are coming to the L-beam, here the edge beam, you can see the edge beam where slab is only on the one side. So since the slab is only on the one side, the slab is not on the another side. So only the 50% of the slab will be helping to resist the moments in the beam. So this resembles the shape of the L. So inverted L. So that's why it is called as the L beam. So we have seen exactly what the T beam and L beam is. So from the geometrical point of view, we are not casting any T-shaped beam, or we are not pouring any concrete over there. It is the combined action of the slab and the beam. So the beam and slab when casted together, so a new action will be generated. That action I can consider as the T-beam action. So let us see the condition. So one by one condition. So there is some condition for this T-beam action to exist. First one, so which I already explained. So what is that first point is the slab, this slab and the beam should be monolithically casted, means it should be casted together. So that's what happening in the most of the construction site. So almost the beam and the slab will be casted together. So R, the slab and beam can be separately casted. So example is precast units, they can be separately casted, but both should be joined together. The slab and the beam should be joined together with 100% fixity. So it should be fixed such that both will be acting together. In such condition, T-beam action will be there. So first one, it should be casted together, or it should be effectively bonded by any other manner. So the code will tell like that, it should be effectively bonded. So bond ಮಾಡಪ್ಪ ನೀನು ಸ್ಲ್ಯಾಬು ಮತ್ತು ಬೀಮ್ನ ಹೇಗಾದರೂ ಬಾಂಡ್ ಮಾಡು, so that they will act together ಅಂತ ಹೇಳುತ್ತೆ. Second point is the slab should be at the top level of the beam. So see here in the T-beam, the slab is at the top level of the beam. So only when the slab is at the top level of the beam, there will be a T-beam action. Because see, this beam will be in the sagging at the center, actually it will be sagging, but the slab will be creating a arcing moment. So since the slab is actually, beam is actually sagging and the slab is actually arcing, the slab will try to hold the sagging beam. So there is a difference in the moment, means this is sagging moment and this is arcing moment and this is sagging moment. Since there is different kinds of the moment, so there will be a resistance. So this will help in actually T-beam action. So if the slab is constructed at the bottom level of the beam, actually the moments will be of the same nature and the slab will actually try to pull the beam, and the T-beam action nowhere exists. Actually you should design it as a beam. So some cases this also will be happening. So inverted beam. So in some cases we will be constructing a inverted beam, so where the slab will be casted at the bottom level. So second condition is the slab should be at the top level of the beam. The third condition. So the third condition is if the main reinforcement of the slab, see this is the main reinforcement of the slab, if it is parallel to the beam, if the main reinforcement of the slab is parallel to the beam, then actually the transverse reinforcement should be provided. The transverse reinforcement should be provided and it should be at least 60% of the main reinforcement, means minimum of 60% should be there at the center of the center. The transverse reinforcement should be at least 60% of the main reinforcement at the center. So this is the third condition. This is actually in the IS code also. You can look at the IS code. So you can see in the next slide this one. So three conditions: that beam and slab should be monolithically casted, beam and slab should be effectively bonded, transverse reinforcement should be provided. If the main reinforcement is parallel to the beam, slab should be at the top level of the beam. And the fourth condition is near the support where arcing moment is there, T-beam action does not exist. Means near the support, this support condition, so where the arcing is there, see there is a negative moment in the beam, so actually the slab will also be creating a negative moment at this location. There will be no T-beam action. So it should be designed as a normal beam or a doubly reinforced beam. So near the support where arcing moment is there, T-beam action does not action. Just have a look at the necessary conditions. So these are the necessary conditions which should be there in order to have the T-beam action. So next point. So I will put few slides. So in some situation T-beam action will not be there. So here actually this is another nice picture. So where you can see the beam with the reinforcement with the stirrups and all. So and it will be connected to the slab. So this is the actually reinforcement made ready. So and you are going to pour the concrete and concrete will be set. So and it will be after 28 days it will be almost ready to carry the load. See in the another two slides here, actually no T-beam action in bracing of water tank, plinth beam and the lintel beams. See here you can see the bracings in the water tank. See this beam, this is simply a beam which is connecting between the columns. There is no slab in between. So this beam will be designed normally as the beam. So which you have seen already in the analysis of the beams. So and here see at the ground level, so there is a this one plinth beam. So this plinth beam will be not connected with any slab over here because slab is not required. So we are going to construct from floor on the ground level by just filling the concrete. There will be no reinforcement. So here the beam will be designed as normally as the beam. There will be no T-beam action. So the lintels are there where openings are provided. So you have to provide the lintels. So there also T-beam action won't come into picture. They are the few examples. So next here in this picture let us see some designations of the T-beam and the L-beam. So actually a cross section is taken in the slab. So you can also see the view of the cross section, projected view. So actually see in T-beam the slab is there on both the sides, means on either side there is a slab on both the sides. Here BF is the effective width of the T-beam. Effective width of the T-beam. BW is the width of the web, or it can also be called as the width of the rib. So here depth is the D is the depth of the L beam, or depth of the effective depth of the L beam, or effective depth of the T beam. DF is called as the effective depth of the flange. See, this T beam is also called as the flanged section. So generally we'll call it as a flange. So flanged section or the T beam section. L beam also can also be called as the flanged section or flanged beams. So this BF is the effective width of the L beam. So here you can see the support, wall support or anything, column support or wall support. So and if you come here, this L0 is the length, that is the length of the this one beam between the points of zero moments. So L0 is the length between the points of zero moment, means where the sagging is there, so where no arcing is there. In simply supported beam, effective length will be the almost the length of the beam. In continuous beam it will be around 0.7 times the L. So this is about the different designations of the T beam. In this picture, so we can see the slab and the beams. So here we have taken the cross section. So we have seen the designations, different designations of the T beam, and also the T beam action, so and the necessary conditions required for the T beam. Let us see how the stress varies. So how the stress varies actually in the your slab. So if I take the cross section, the stress is actually varying like this, means there is a sagging at the center and gradually it will be arcing near to the beam location. So in the last slide we have seen that BF is the effective width of the T beam. So actually while explaining the sentence I have told that so the T beam will be acting so from the either left side and the right side of the beam, so from the center of the slab. So here you can see that so actually this is the actual width of the T beam. So that is S1 is the span of this beam, span of the slab, and S2 is the span of this slab. So S1 plus S2 divided by 2. So will be the distance between the from the midpoint of the left side of the slab to the midpoint of the right side of the slab. So this distance, this S1 plus S2 by 2 is the actual width of the T beam. But we are going to define a effective width of the T beam. Why? Because see here the stress variation here actually is complex. So it is not uniform. So it is not linear. So it is complex. It is difficult to calculate the amount of this one stress. So in order to calculate the stress, we are going to make a assumption that in the effective width in this BF, the stress will be acting uniform. So this blue color line where the stress is acting going to uniform will be equal in magnitude for this stress. So the stress from the S1 plus S2 by 2. So this stress and this stress will be equal. So that's why in order to make the calculation simple, so we are going to give the effective width of the T beam. So rest of the designations we know. So DF depth of the flange, PF is the effective width. So D is the actual depth of the beam. So effective width of the flange. So last time in the last slide we have seen so how the stress is going to variation. We will see by using the formula how to calculate the effective width. So this is the stress variation, actually non-linear or complex. So this blue color line is the assumed stress distribution, so which will be uniform. So from page number 37 in the IS 456, so codal provisions is there. So effective width for the T beam is calculated as L0 by 6 plus BW plus 6 times the DF, where L0 is the, I have already told, that is the distance between the points of zero moments. So where there is a zero moment, the distance between the points of zero moments. So BW is the width of the web. So DF is the depth of the flange. So by substituting here in this formula, we can get the effective width of the T-beam. So for isolated T-beams, what is this isolated T-beam is? See, the slab is projected on left and right, but it is not continuous. So here we have shown the continuous symbol here and here, but the slab is ending here only. Means you can take an example of the bus stop. Some bus stops we can see there will be a slab projected on both sides. Center there will be a beam, and the slab will be projected on both sides. So that can be taken as an example for isolated T-beam. So the slab will be projected on both the sides, but it will not be continuous. It will be ending at some distance. So for that isolated T-beams, so L0, once again it will be the same, that is the distance between the points of zero moments. So same L0. V is the actual width. So this is the actual width. So don't consider this discontinuous line. Don't consider this continuous symbol. So here actually it is ending. So P is the actual width plus PW. So if you can substitute this one, so we will get the effective width for the isolated T-beams. So next for L-beam. So effective width is calculated by, so you know what L-beam is. So the slab is only on the one side of the P. So that is the L-beam. So but the slab will be continuous. It will be connected to the adjacent beam. So L0 by 12 plus BW plus 3 times the DF. The same designations holds good. For isolated L-beam means, actually this is a isolated T-beam. You can see a T-beam. So it is a deck slab provided for connecting from one end to the another end. So we are not able to see the another end in the picture, but there is a beam and there is a slab on both the sides. So this can be called as the isolated T-beam example. But if there is a beam and there is a slab only on the one side and it is discontinuous, it is stopping at this location, that type of beam can be called as the isolated L beam. So to calculate the effective width of the isolated L beam, so it is 0.5 times the L0 divided by L0 by B plus 4 times plus the BW. So all these equations to calculate the effective width of the T-beams is given in the IS 456. So you can go to the page number 37. So you will get these formulas. So we'll go to next slide. So rules for analyzing the T-beam or designing the T-beam. So what are the rules, let us see. So actually we will classify here only in the two cases in order to make it simple. So first case is neutral axis lies within the flange. So in single reinforced, in beams you have seen the neutral axis. So you are known how to calculate the neutral axis. This neutral axis is lying in the flange. See, so this is the flange section where DF is the depth of the flange. So you can see that the neutral axis is lying in the flange section. So means the strain is varying like this linearly and becoming 0 here. So maximum strain of 0.0035 in the extreme end of the fiber is, and up to 0.002 the stress in the concrete will be uniform. So I think everyone know this one, so but I will explain once again. So from this strain 0.0025 to 0.002, actually the stress variation in the concrete will be uniform. So it will be in the rectangular part. So the IS code assumes like this. So and in the remaining down portion actually it is parabolic. So that's why we call the stress variation in the concrete is partly parabolic and rectangular. So it is rectangular from the 0.0035 strain level to 0.002 strain level. So in this region the stress will be actually in the rectangular shape. and the remaining portion it will be actually in the parabolic shape. It will be non-linear. So once again we'll come back. So just I was explaining about the stress variation. So this stress variation will be similar for the T-beam, will be almost similar as a normal beam. So we'll see the neutral axis lies within the flange. So when the neutral axis actually lies within the flange, we can tell this as this is not a T-beam. This is a beam of width BF and the depth D. So from here to here the depth dy, because actually above the neutral axis whatever the concrete is there, that will be actually contributed to the carry the tension force. So below the neutral axis whatever the concrete is there, it is assumed that the concrete will be cracked and it will be no more carrying the tension force. Since the concrete is weak in tension, so we are going to provide the reinforcement. So this concrete, wherever whichever is in the neutral, below the neutral axis, it will be cracked and it will not be contributing, just it will be acting as a bonding media. So whatever the tension force will be carried out by this steel, so this steel will be going to carry the tension force. That's why when the neutral axis lies within the flange, we can call it as the T-beam as can be taken as a normal beam whose width will be equal to the effective width of the T-beam and the depth will be the D. So it is a beam of width BF and the D, effective depth is D and the total depth will be the D. So I hope you got this one. So ಇಲ್ಲಿ ನೋಡಬೇಕಂದ್ರೆ ಸೊ ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್ ಸೊ ನಿಮ್ಮ ಫ್ಲ್ಯಾಂಜ್ ಒಳಗಡೆ ಇದ್ದಿದ್ದರಿಂದ ಏನಾಗುತ್ತೆ, ಸೊ ಇಲ್ಲಿ ಇದನ್ನು ನಾರ್ಮಲ್ ಬೀಮ್ ಥರ ಕನ್ಸಿಡರ್ ಮಾಡ್ಬೋದು. ಸೊ whose dimension is BF and the depth will be the D. So the procedure for this one will goes like this. First one we will calculate the XU. So this XU will be calculated, means that is the depth of the neutral axis, will be calculated using this formula 0.87 Fi AHT divided by 0.36 times the B into FCK. So once you get the XU, so you will check that it is less than TF. So if you go to previous slide, the XU will be less than the TF. So if it is happening, then assumption is correct. What assumption we made? That the depth of the neutral axis will be below the depth of the flange neutral axis. So that assumption is correct. So we will note down the what is the XU max value. So you know 0.48 times the D for steel, this one 450 Fe 450. So 250 also we have the XU max value. So we can get it from the IS code. So we will calculate the XU max. So if the XU is less than XU max, then this section is under reinforced. If it is greater, then it will be a over reinforced section. So the moment of resistance will be calculated using the formula. So if you see these equations, we have already gone through this equation. So this is normally the beam equation. So whatever we have assumed means the T-beam will be, it is a beam of width BF and depth D when the neutral axis lies in the flange. That's why the same formula hold puts here. So where this B can be taken as the equivalent to BF, that is the effective width of the beam. So case 2. So in case 1 neutral axis was lying inside the beam. In case 2, neutral axis lies below the flange. So here is the flange. So below this, the neutral axis is going to lie. So step 1. So we are already done actually. So we will calculate the XU, assuming first the neutral axis lies in the flange. So if XU is greater than this one, the same condition we are actually assuming. So we will go to the step 2. So we have to calculate the XU value when the neutral axis lies below the flange. So for this there is a relation by equating the compression force. So total compressive force is equal to the total tensile force, where C1 is the compressive force of the web region. So this is the web. So in the web region we are going to calculate the compression force. So this is same as your normal beam formula. So where compression is given as 0.36 FCK XU into PW. This is the width of the beam. So in your normal beam section, BW will be taken as B. Generally here actually B is equal to BW. C2 is the compression force in the remaining part of the flange, because this part of the beam is already considered in C1. So the remaining flange is BF minus BW. So that width we are going to be considering over here. So here actually the stress will be uniform. That's why we have taken 0.45 FCK. That's the assumption, 0.45 FCK BF minus BW into the depth of the flange. So by using this equation we are going to calculate the compressive force in the remaining part of the flange section. So T is the tensile force, you know, that is calculated as 0.87 times the Fi into the AST. So we are going to substitute this one in the equation and we are going to solve for the XU. So once you get the XU, so you are going to check this whether DF by XU is less than 0.43. If XU is greater than DF, means whatever the XU calculated from this equation, if it is greater than DF, then the assumption is correct. So assuming DF by XU is less than 0.43, that assumption is correct, and actually we are going to be the next step, step 3. If XU is less than the DF, then there will be another picture, so which you are going to see in the next slide. But let us come and have a brief look on the strain variation and the stress variation when the neutral axis lies below the flange. So I have already explained how the same stress variation and the same strain variation will also be happening, but just have a look. Let's have a look. See here, the neutral axis is lying at this here. So the maximum strain 0.0035 will be at the extreme fiber, so generally as the beam. Here the strain 0.002 will be actually below the flange section, so will be below the flange, and the stress variation is also same from 0.0035 to 0.002. The stress variation will be uniform, so that it will be rectangular, so of magnitude 0.45 FCK. So you can see here, that's why you are taken as the 0.45 times the XCK. So and below this portion there will be a parabolic stress variation. So this you have to note it down, that 0.002 strain level will be the below the flange level. See, I told if XU is greater than DF, then the assumption is correct, and then we will go to step 3. If XU is less than the DF, then actually we have to recalculate this XU. How we are going to recalculate this one, we are going to see in the next step. See, if XU is less than DF, then DF by XU will be greater than 0.43. So let us recalculate the XU by equation this one. Here actually equation only C2 will be changing. Instead of the depth of the flange, we will be writing a new term called as the YF. What is this YF? Actually YF is given as 0.015 times the XU plus 0.65 times the DF. See, here you can see the strain variation when this one, neutral axis is lying below the flange level, but the 0.002 strain level will be occurring at the flange section, in the flange location. Then what happens is actually the stress will be partly parabolic and partly rectangular in this flange also. That's why we are going to calculate this YF. So what is the distance of the YF? So YF is given by 0.15 XU plus 0.65 times the DF. So we are going to substitute the YF here. So So after substituting this one, so we'll calculate once again, we'll solve for the XU. So then we will obtain the XU. So step 3 actually, so we were told earlier, so if that is passed we have to directly go to the step 3, otherwise we have to recalculate the XU by using this formula. So where we have to come to the step 3. So in step 3 we will combine the XU with the XU max. If XU is greater than XU max, then the section is over reinforced, or it can be balanced. When it is equal, it will be balanced. Then we will if it is greater, then we will check this value, df, that is the depth of the flange, divided by the effective depth of the beam, so is less than or equal to 0.02. Then use the equation G 2.2, page 96 of IS 456. So in page 96 in IS code, they have given this equation. So by using this equation, we are going to calculate the moment of resistance of the section. So this is the equation. So you know almost all the designations over here. So XU max is the so XU max is the this one, maximum depth of neutral axis, and is the depth. So XU max, once again, BW is the depth of the web. So FCK, characteristic strength of the concrete. BF is the effective width of the flange. So DF is the depth of the flange. So you know all the designation. We have to substitute in this equation, and we have to calculate this one. So if DF by D is greater than 0.2, then what is the difference? Actually, this DF is replaced by the YF. So we know the formula already for the YF. Wherever the depth of the flange is there here, so that will be replaced by YF, and this YF is given as 0.15 times the XU plus 0.65 times the DF, and it should not be greater than the DF. If you calculate this one, it should not be greater than the DF. So in step 4, so actually we calculated when the section is over reinforced or balanced. So we'll go to step 4, if XU is less than X max. So here we calculate this one. If XU comes out to be less than this, then we don't need to do this calculation. We'll directly stick to this calculation. So where XU is less than X max and the section is under reinforced. In most of the cases, the section will be under reinforced. So if it is under reinforced, then we are going to check this condition. DF by XU should be less than or equal to 0.43. Then we will use the same equation G 2.2 of page 96 IS 456. So here the same equation we are going to use, but XU max will be replaced by the XU, that is the depth of the neutral axis. So depth of the neutral axis. So the rest of the formula will remain the same. So replace wherever here XU max is there by XU. If DF by XU is greater than 0.43, then we will go to the equation G 2.2.1. So in page number 97 of IS 456, so sorry, it is written as 976, actually it is 97. So by replacing XU max by XU value. So once again same thing, here whatever the equation we have written XU max we will replace by the XU. So on this YF remains same, so XU max will be replaced by the XU. So on YF value will be this one. So this is the equation to calculate the moment of resistance of the section for under reinforced section. I have given you the clip of from the IS code. So in the IS code, actually annexure G, so in page 96, so there is a heading called as the flanged section. So in flanged section C, in G 2.1, if XU is less than DF, then the moment of resistance may be calculated by the equation G 2.1.1. This is actually the case 1. So if XU is less than DF, then we are going to use this formula. So to calculate XU, we are going to use this formula. To calculate the moment, we are going to use this formula. See, this is the rectangular section. So the moment of resistance of the B can be calculated by this equation. The same equation will be used over here when XU is less than DF. When XU is greater than DF, then the condition is different. See, if the DF by D does not exceed 0.2, if it is less than 0.2, so which condition is this? This is actually in the case 2, step number 3. So when the section is over-reinforced. So this equation is given in the page number 96. You can go directly and pick the formulas. There is no need to remember or by heart. So all the designations are given over here. So if df by d does not exceed, means less, if df by d is more, then it is given in the next page. So here this is the equation. See here you can see the yf. So same thing, df will be replaced by the yf, and yf value will be given by this one, 0.15 times the xu plus 0.65 times the df. But if the section is under reinforced, for that also here they have given. So if xu max is greater, means that xu is less than df and xu is greater than df. So we have to calculate df by xu, and if it is less than 0.43, use the equation G2.2. G2.2 means that is the previous slide. This equation we will use, but replace xu max by xu. So that equation we are going to use, and G2.2.1 when df by xu exceeds the 0.43 value. So this link I have shown, you can use it directly. So these are the theory part. So where how to calculate this one, rules for designing the T-beam, and we have seen gone through the steps. Okay, so we'll look at a single problem. So the problem is like this: and singly reinforced slab 120 mm thick is supported by T-beam spaced 3 meters center to center. The width of the rib is 450 mm and effective depth is 580 mm. So mild steel reinforcement 8 bars of 20 mm dia have to be provided in tension in 2 layers. The effective cover to the steel bar is 50 mm. The effective span of the simply supported beam is 3.6. So grade of the concrete M15. So we'll read the problem and also we'll write down the data. So actually, so here first we can see a singly reinforced slab depth is df, that is the depth of the flange, is 120 mm. Next, spaced 3 meter center to center, means the slab is spaced 3 meter center to center. So actually we don't require this data, that's why we have not written over here. The width of the rib, that is BW, width of the rib or the width of the web is 450 mm, and the effective depth, that is the small d, effective depth is the small d, 580 mm. So they are given the steel details, so which I have written in the next one, the 8 bars of 20 mm dia. The effective cover, so cover they are given 50 mm. The effective span, that is the small L, so of the simply supported beam, this L is equal to L0, so it is 3.6 meter. So all those things we have taken down. So we have to calculate the depth of the neutral axis and moment of resistance MR. So FCK, so 8 bars of 20 dia. So in order to calculate this one, area of the steel, it is pi d square by 4. So since it is 8 bar, so 8 into pi d square by 4. So if you calculate this one, so the area of the steel will be 2513 millimeter squares. So this area of the steel we have calculated. So next we have to calculate the effective width of the flange. Since they are not given here directly, in most of the problems they will be given, but here they are not given. So we will calculate it using the formula, effective width formula, that is given by L0 by 6 plus BW plus 6 times the DF. So this equation is in page number 37 of IS 456. So if you go there, we will get that equation. So substitute, so we are going to substitute in meters only, 3.6 since it is a simply supported beam, so it is the point between the points of zero moment. It is the distance between the points of zero moments. So 3.6 by 6 plus BW, so 450 mm you have to reduce to the meter, so divide by actually 1000. So if you divide by 1000, it is 0.45 plus 6 times the df, so depth of flange 120 mm. So if you convert it to the meter, so once again millimeter to meter conversion is dividing by 1000. So 1000 ಇಂದ ಡಿವೈಡ್ ಮಾಡಿದ್ರೆ ಮಿಲಿಮೀಟರ್ ಇಂದ ಮೀಟರ್ಗೆ ಕನ್ವರ್ಷನ್ ಮಾಡ್ಬೋದು. ಸೊ ಇದು ಸಾಕಷ್ಟು ಜನಕ್ಕೆ ಗೊತ್ತಿರಬೇಕು. ಸೊ ಇಫ್ ಯು ಗೋ ರಾಂಗ್ ಇಯರ್, ಸೊ ದ ಪ್ರಾಬ್ಲಮ್ ವಿಲ್ ಬಿಕಮ್ ಎಂಟೈರ್ಲಿ ರಾಂಗ್. ಸೊ ಯು ಕಾಂಟ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಓವರ್ ದೇರ್. ಸೊ ಮೀಟರಲ್ಲಿ ಎಲ್ಲ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ. So we will get the effective depth 1.77. So next we have to calculate the depth of the neutral axis. First case assumption is the neutral axis lies within the flange. So for that, to calculate XU, so we have the formula. So this formula is in page number 96. So we have taken the formula from the page, from the AS code. We write down the formula. So 0.87 Fi, they have given the steel grade 250 mm. AST we have calculated, see it is in millimeter square, so 2513. 0.36 B, B is the actual width of the flange, or the effective width of the flange. Actually effective width and the actual width will be the same when the neutral axis lies within the flange. So we have seen that. So we are going to substitute this in millimeter. So from meter to millimeter we have to multiply by 1000. So multiply by the FCK is 15. So solve the numerator separately and the denominator separately, and if you divide it you will get 57.19 mm. So this is the XU value. See, this XU value is less than DF. What is the value of DF? DF is 120 mm. So 57.19 mm is less than the 120 mm. So the neutral axis lies within the flange. So over. So we have calculated the XU value. So the steps ends here. Then what we have to calculate? We have to calculate the moment. If XU was greater than DF, then we have to move to the step number 2. So assumption is correct. So we calculate the XU max. So since it is a 250 grade steel, so XU max is 0.53 times the D. So you have seen in the theory. So 0.53 into the depth is 580 mm. So if you multiply these two, we will get 307.4 mm. So since XU is less than XU max, the section is under reinforced. So we are going to write down this equation to calculate the moment of resistance of the section. So this is also in page number 96 of IS code. So we will write down the equation. So 0.87 Fi into AST into D. So this equation we will write it down. I am going to substitute this one. So Fi, grade of the steel 250, and AST is 2513.27. So which you have calculated. D is the effective depth 580. 1 minus once again AST we are going to substitute. Fi is 250. BF is nothing but the B or BF which are calculated. So it is in meter, we have to convert it to millimeter and substitute. Meter to millimeter conversion is multiplying by 1000. So D is 580 mm. So FCK is 15. So if you solve this equation, then we are going to moment of resistance as 304.11 into 10 to the power 6 Newton millimeter. So or 304 kilonewton meter is the moment of resistance of the section. So this solves the problem. So the required answer is obtained. So moment of resistance of the section and the depth of the neutral axis, both have been calculated. So we will continue the problems. We will get more problems, that is the case 2 problems, in the next section. So now we will see some multiple choice questions, so that you can recap. So whatever we have explained here, So you can just recollect those things. So multiple choice question. First one, a T-beam behaves as a rectangular beam of width equal to its flange, means that is the BF. If the neutral axis, I think you all know the answer. So when the neutral axis remains below the flange, no, neutral axis when it remains within the flange. So if it remains within the flange, then T-beams behaves as a rectangular beam. So I have told you many times this one. So this will be a simple question. Next, second one, for T-beam action to exist. So for T-beam action to exist, beam and slab should be monolithically casted. Beam and slab should be casted separately. If it is casted separately, with T-beam action will be there. If effectively bonded together, means beam and slab should be effectively bonded together, both A and C. So A and C will be the correct answer. So option will be the D for the second question. If the T-beam is under reinforced and the neutral axis lies in the web, the stress in the flange is uniform only if, say, the T-beam is under reinforced and the neutral axis lies in the web. Then the stress is uniform. So uniform means in the flange section the stress is uniform only when dF by XU, where this is option 1, dF by XU is less than or equal to 0.43. You have to remember the step number 4. So where we are going to calculate dF by XU, then only it will be uniform. If the neutral axis lies in the flange, a T-beam can be treated as a rectangular beam. If the neutral axis lies in the flange, a T-beam can be treated as a rectangular beam of BW. This is width of the web into the depth. Is it correct? No. Width of the flange into the D. None of the above. BF into D. See, this one we have to take it out because cover also should be included. This will be the BF will be the width. Total depth of the beam will be capital D. This D is effective depth. This is for calculation purpose. But we should, whenever we are telling the beam depth, we will be telling the overall depth of the beam. So width of the beam into the depth of the beam, capital D. So fifth question, in the effective width of the flange formula, L0 defined as the distance between the points of zero moment is considered due to beyond L0 the beam is in arcing and hence the flange will be in the tension and ineffective. This sentence straight away is right because as we have already told, near the support section there will be arcing and the T-beam action won't come into the picture. So beyond L0 the beam is arcing and hence the flange will be in tension and ineffective. Exactly correct. So within L0 the stresses are uniform, so not necessary. So strain compatibility, none of the above. So the option is first one. For T-beam action, slab should be at bottom of the beam, middle of the beam, top of the beam, at CG of the beam. So this is straight answer, so it will be at the top of the beam. T-beam action exists in lintels wherever the opening is provided, plinth beam, so near the foundation level, bracings of water tank, slab and beam casted together. So slab and beam casted together will be the answer. If the slab is connected to the one side of beam, such a beam is called as T-beam, doubly reinforced beam, L-beam, under reinforced beam. Say slab is connected to the one side of the beam. So one side of the beam only slab is there. So then that is the L-beam. If the slab is connected on both the sides of beam, such a beam is called as the T-beam. Both sides of the beam slab is there. So just recapping. So this multiple choice question will help you to recollect. In continuous beam, the moment near the support is what? It will be arcing. So once again I have given the answer here, so you can note it down. So references, these are the references which we have referred. So thank you, that ends with the today's session. Thank you everyone.